Hello, welcome to another module in this massive open online course. So, we are looking at the Fourier transform and in particular looking at the frequency response of ideal filters. So, let us continue that discussion. We have looked at the ideal low pass and high pass filters. We also want to look at what we are going to look at next are the ideal band pass and band stop filters. Okay. So, let us continue our discussion on the concept of ideal filters, okay, and we want to look at the notion of an ideal band pass an ideal band pass filter, as the name implies, allows only frequency components of a signal within a certain band to pass through and suppresses or blocks all other frequency components which do not lie in this band, all right. So, let us say the band is omega 1 to omega 2, we can call this as the pass band. Then we have magnitude for this band pass filter, we have magnitude h of omega equals 1 for omega 1 less than mod omega, magnitude omega less than omega 2 and 0 otherwise. Okay. So, it allows only frequency components which lie within this band either omega 1 to omega 2 or minus omega 1 minus omega 2 to minus omega 1 to pass through. So, we have this band which is either omega 1 to omega 2. So, it has a gain of 1 or minus omega 2 to minus omega 1. So, allows, so what this does is it basically allows only band of frequency, allows only frequency components in the band omega 1 to omega 2 to pass through, and this is also known as the pass band, that is omega 1 to omega 2. This is also known as the pass band. Okay. And this is a band, this is an ideal band pass filter, and the opposite analogously we have an ideal band stop filter which basically stops all the or blocks all the frequency components belonging to that band and passes or allows undistorted transmission of all the other frequency components which do not lie in this band, all right. So, we have also a band stop and in the band stop filter you have, well, you have, let us say omega 1 to omega 2 is the stop band, then you have all the frequencies in this band which are blocked, and that is gain is 0 in this band and all other frequencies pass without distortion. So, these are the stop bands. So, omega 1 to omega 2 is the stop band. So, the band stop filter is magnitude h of omega. So, it is characterized by the frequency response magnitude h of omega equals 0, omega 1 less than mod omega less than omega 2, and this is 1 otherwise. Okay. So, this is 1 and this is 1 otherwise. So, these are the stop bands, alright. So, this basically blocks all frequencies that belong to the band omega 1 to omega 2 or minus omega 2 to omega 1. So, blocks all frequencies omega 1 to omega 2 minus omega 2 to minus omega 1. Okay. So, it all blocks all the frequencies in these bands. Okay. And further, we have only talked about the magnitude response, but we have not talked about the phase response. But we know that to avoid distortion, for a distortionless response, the phase response has to be linear. Okay. So, although we have not specified on the phase response, you can note that the phase response has to be linear to avoid distortion. Okay. So, we can say to avoid distortions, all these filters, all these ideal filters should have a linear phase characteristic. These should have a linear phase characteristics. Remember, for a distortionless LTI system simply attenuates and delays the signal corresponding to that is if the input is x t, the output is k times k x t minus t d, t d is the delay, k is the scaling factor. Alright. So, the phase response of that is the magnitude response is k, the phase response is minus j, that is minus omega t d, that is the phase, okay, which has a linear characteristic in omega. Alright. So, that is basically characterizes a distortion. Okay. So, now so far we have looked at ideal filters, but of course, it is difficult to design such ideal filters, as I said, with such sharp cutoffs. So, naturally we have to rely on non-filters that are non-ideal to a certain extent. So, let us also look at one of the basic non-ideal filters, one of the basic low pass, non-ideal low pass filter, which is formed by a simple RC circuit. Okay. So, we want to look at a non-ideal frequency selective filter. Let us look at a non-ideal low pass filter, okay, which you can say is simply given by this RC circuit. The simplest, so let us say simplest low pass filter, let us say x t is the input voltage, y t is the output voltage. Let us look at the relation between x t and y t. So, this is an RC circuit, a simple, and we have, let us say, if we have this, if we call this, if we denote this current by I t, then we have x t, the voltage is voltage drop across the resistance, which is I t times R, plus the voltage drop across the capacitance, which is y t, but we know the current across the capacitor is C times the derivative of the voltage across the capacitor, that is a dy t over dt, which basically implies, now substituting this expression for I t over here, we have the expression x t equals R c dy t over dt plus y t. This is a constant coefficient differential. You can see this is the constant coefficient differential equation which characterizes the LTI system. Okay. This is a constant coefficient differential equation for the LTI system for the RC circuit. Now, if you take the Fourier transform, then we have x of omega equals RC. Remember, the Fourier transform of the derivative is j omega times the Fourier transform of the signal. So, j omega times y omega plus y omega, which is y omega times 1 plus j omega R c. Okay. And now, therefore, if you look at y omega over x omega, so which is nothing but the frequency response, that is basically you can readily see that this is given as 1 over 1 plus j omega R c, 1 over 1 plus j omega R c, which is basically I can also write this as 1 over 1 plus j times omega over omega naught, where omega naught equals, now you can see omega naught equals 1 over R c. Okay. So, for an R c circuit, I can represent the frequency response as 1 over 1 plus j omega over omega naught, where omega naught equals 1 over R c. Okay. So, basically that is the omega naught is 1 over R c. Okay. And now, if you look at the magnitude, now let us look at the magnitude response of this. The magnitude of this is 1 over 1 plus or 1 over 1 plus omega over omega, or 1 over 1 plus omega or omega naught square under root, that is the magnitude response of this. And therefore, magnitude h of omega square, if you take the square of the magnitude response, that is nothing but 1 over 1 plus omega square divided by omega naught square. And if you look at the magnitude response, you will observe that if you look at the magnitude response, it is easy to see something, that is at omega equal to 0, magnitude h of omega square equals 1, omega tends to infinity implies omega square tends to infinity. So, 1 plus omega square over omega naught square tends to infinity. So, 1 over 1 plus omega square over omega naught square tends to 0. So, magnitude h of omega square tends to 0, and therefore, this is 1 at omega equal to 0, and as omega tends to infinity, it tends monotonically to 0. Similarly, as omega tends to minus infinity, it tends to 0. So, you can basically see this has peak at omega equal to 0, it has a maximum gain of unity, and both sides, alright, it decays to, that is omega tends to infinity, omega tends to minus infinity, it decays to, the gain of the filter decays to 0. So, this is clearly a low pass filter and non-ideal low pass filter, okay, because it does not have any sharp edges, but it is smoothly decaying to 0, the gain is decaying to 0 as omega tends to either minus infinity or infinity. So, this is basically your non-ideal low pass filter. This is a non-ideal low pass filter and it tends to 0 as omega tends to infinity, and again here also tends to 0 as omega tends to minus infinity, and this is basically the maximum gain, which is unity. Okay. And of course, what we would like to do is we would like to characterize the bandwidth of this filter, but because it does not have any sharp edges, we cannot clearly characterize what is the cutoff frequency, right, what is the stop band and what is the pass band, as we did for the ideal filters. Therefore, we would like to develop measures and metrics to characterize the bandwidth of this filter. One such metric is what is known as the 3 dB bandwidth. Okay, the way to characterize the bandwidth of this filter, the pass band and the stop band, is what is known as the 3 dB bandwidth. Okay, so we want to define the 3 dB bandwidth of the filter, omega 3 dB. The technical definition of this is value of omega such that and the power of the filter, you can say, the power decreases by a factor of half, when compared to the peak. Implies the amplitude decreases by a factor of 1 over root 2. So, this can be understood as follows. What we want to show is that if at the peak the amplitude, all right, the amplitude of the transfer function, of the amplitude of the frequency response is at the peak, if the amplitude of the frequency response is, let us say, k, all right, then at the 3 dB point the amplitude decreases by a factor of root 2, that is, it is k over root 2, and therefore, if the amplitude decreases by a factor of square root of 2, the power, which is the square of the amplitude, decreases, is basically a factor of half in relation to the power at the peak. Okay. So, basically what this implies is that if you look at the, and of course, for the previous low pass filter, you can see the peak occurs at 0, and in fact it is, the gain is unity. So, we have magnitude h of 0 equals 1, which implies at the 3 dB point we must have magnitude h of omega 3 dB equals 1 over square root of 2, which implies magnitude h of omega 3 dB square equals half. Basically, it is all related to the amplitude at the peak. So, this is, you can say, half 1 over root 2 into 1. So, this is half into 1, which is nothing but half. And now, you can see magnitude h of omega 3 dB square equals 1 over 1 plus omega square by omega naught square, which is equal to 1, omega naught square omega 3 dB, which implies omega 3 dB square by omega naught square equals 1. I am sorry, this is equal to half, which implies omega naught square by omega 3 dB square, which implies omega 1 plus omega 3 dB square by omega naught square equals 2, which implies omega 3 dB square omega naught square equals 1, which implies very simply that omega 3 dB equals omega naught, which is nothing but this is equal to, remember, this is equal to 1 over RC, correct. So, omega 3 dB equals omega naught, which is 1 over RC. So, the 3 dB bandwidth of this low pass filter, you can think of this as the approximate cutoff frequency of this low pass filter, is defined as, that is one of the ways to define the cutoff frequency of this non-ideal low pass filter is 1 over RC, where R is of course the resistance, C is the capacitance. Okay. And why is this known as 3 dB? And the relation is obvious, because if you look at the power, that is magnitude H 3 dB square equals half. So, if you look at the decibel value of this, that is 10 log to the base 10 magnitude 3 dB square, or 20 log to the base 10 times the magnitude, that is equal to 20 or 10 log to the base 10 of half, which is equal to minus 3 dB. You can say this is approximately minus 3 dB. So, the 3 dB magnitude, the 3 dB, okay, the 3 dB point, at the 3 dB point, the output power of the signal is attenuated by 3 dB, correct. At the 0 frequency, remember the gain is 1, the magnitude is 1, the power is also 1, alright. At the 3 dB point, there is a 3 dB frequency, the magnitude decreases by a factor of root 2, that is 1 over root 2. So, the power decreases by a factor of half. So, in decibel values, the power decreases by a factor of 3 dB or minus 3 dB. So, therefore, this is known as the 3 dB frequency. So, 3 dB reduction in this. So, 3 dB reduction in power. So, this gives you a 3 dB reduction in power, okay. Hence, it is known as the 3 dB point, and the 3 dB bandwidth is 1 over RC, that is what we have seen, okay. So, the 3 dB bandwidth of this RC circuit, of this non-ideal low pass filter, is 1 over RC, okay. Let us look at a few other aspects. Now, we can also define the signal bandwidth. So far we have defined the bandwidth of a filter. We can also use the same definition to define the bandwidth of a filter. The bandwidth of a filter, to define the bandwidth of a filter, of a signal, let us say we have a signal xt that has a Fourier transform x of omega, 3 dB bandwidth omega 3 dB equals the frequency omega such that we have magnitude x omega or magnitude x omega at the 3 dB point equals 1 over root 2, of course, magnitude x of 0, which means magnitude x of omega 3 dB square, which recall is the energy spectral density of the signal, equals half magnitude x of 0 square. And also there is the notion of what is known as a band limited signal. I think something important, a notion of a xt is a band limited signal xt is a band limited signal if, let us say we have the Fourier transform of xt, which is x of omega. Xt is band limited if magnitude of x of omega equals 0 for omega greater than omega m. So, omega m is the maximum frequency, and this plays an important role. We will talk more about this later. So, this is termed as the maximum frequency. So, all the frequency components in the spectrum x of omega for omega larger than omega m, that is omega larger than omega m or omega smaller than minus omega m, are 0. Okay. And you can visualize this as follows. If you have the omega axis, then let us say, okay. So, this is your omega m, this is your minus omega m. So, this is band limited to the signal is, this is your, let us say this is the magnitude spectrum, and this is band limited to omega m. Okay. Band limited signals have an important role to play in sampling and so on. All right. So, this basically more or less summarizes what we wanted to talk about the Fourier transform. We have looked at the various aspects of the Fourier analysis of continuous time signals, starting with first aperiodic signals, looking then also at aperiodic signals, the application of Fourier transform in the analysis of LTI systems, ideal filters, and now also non-ideal filters, and how to characterize the bandwidth of a non-ideal filter. All right. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.